So today, new topic, we will be talking about conformal maps. And I have basically, so obviously it's in the center of the theory of conformally invariant objects. And I will need to give you an intuition about two results, which are the Riemann mapping theorem, and I will say a bunch of results on how to estimate the derivative of a conformal map by knowing information on the domain and the image. So just before starting, so a conformal map is a map which is holomorphic plus bijective. So holomorphic means derivable in the complex sense. So the limit of f of z minus f of z0 over z minus z0 converges to something. For people who are not used to this, that's the same thing as analytic, which means that around every point you can expand as a power series. And even this similitude between these two definitions is not obvious. That's really a theorem. So these two definitions, I guess, that was the introduction or the philosophy of Cauchy, Abel, Weierstrass, and this kind of people when they started this theory. But just a few years later, another mathematician came with another point of view on this function from C to C, and it was Riemann. And he introduced the notion of conformal map. Not exactly this one, but you will see. So what he called a conformal map is a function which preserves the angle. And again, non-trivial theorem, it's the same as a holomorphic plus bijective map. So every time I will be talking about conformal maps, I will be rethinking to holomorphic plus bijective, but the introduction is really motivated by this preservation of angles. Okay? For people who are not used with this, not familiar with this theory, I will use non-trivial theorems about them, about these kind of functions. So come and ask me after for the proof or further explanations. But I will not have time to give them now. But really don't hesitate. And if you have to remember one thing about this theory of complex analysis, is that this definition is very rigid. Somehow it enforces a lot of things on your function. And it's exactly what you will see in this TA. We are going to prove that knowing very few things on, say, the domain or the range, you can deduce a lot of things about the function itself. OK, so the second thing that I will need, U will be always for me an open set. And in this TA, I will consider simply connected open set. So how many people know what is simply connected? Whoa, everybody? No, I cannot ask the opposite question, I guess. But so simply connected, you have two ways of seeing it. Either you take any closed path, continuous path, of course. In your domain, you can retract it to only one point by a continuous transformation. That's the first way. And the way why it's called simply connected is because in dimension 2, at least, I guess in any dimension, it's equivalent to saying that the complementary is connected. So it's something without holes. OK. And so the first theorem I want to discuss, which is due to Riemann, is the following. If you take also U or D, it will depend, will be a domain. So this is usually called a domain. So if I take D and D prime, two simply connected open set, which are not equal to the plane, and we will discuss that later, then there exists a conformal map between them. So I guess it's one of the most wonderful theorem you can find is this area, and I want to discuss a little bit about that. So what does it say? It says if you take two domains, let's say the disk and the most ugliest domain you can imagine, if they are both simply connected, there exists a bijective map which is conformal between them. Okay? So this theorem actually is not due to Riemann, like always. I mean, so in his thesis, Riemann proved a weaker form of that, assuming what we call the Dirichlet principle, so something which is not obvious and which is not even true every time. And basically, it applied to polygons. And it's much, so it was in 1851, something like this. And the proof itself is due to Cobra Function in 1912. Yeah, 1912. So much later, 60 years later. And when it appears in the Riemann monograph, people were really thinking that it was false. I mean, that we won't be able to prove it. And there are simplifications of this Riemann, of the proof of Cobra Function, which is due to Cobra. I say that because you will see that they like to prove each other results, or these guys. So the most elegant proofs are due to Cobra and Ritz. But anyway, so why is it an interesting result? First, because it's unexpected somehow. It's when you look at conditions to be homeomorphic between two sets. Conditions that are sufficient, there are not many. It's very hard to decide if two sets, even open, are no, open it's easy, but are homeomorphic or not. It's easy to prove that they are not. You find a condition that which is, say, preserved by homeomorphism, and you prove that one satisfies it and the other not. But in the case, in the other way, proving a sufficient condition is very hard. Here you have even better. If you restrict a lot the range of possible function you allow, you still have a sufficient condition, which is open and simply connected. The second thing about that is that you really need to be simply connected. If you are not simply connected, if you take two analysts, say, so you take this set and this set, they are not conformally equivalent. So that's not trivial to prove. You need to have what we call conformal radius, but with that, or conformal length, with that you can prove that it's not conformally invariant, but it's not trivial. So you really need to be simply connected. And the other thing which is nice with this theorem is that it extends to what we call the uniformization theorem, which says that now you take any surface, two-dimensional surface, so surface, which is simply connected, then it is conformally equivalent to either C or the sphere or any simply connected domain not equal to C or the sphere, so say the disk. So you have three possibilities when you look at equivalence by conformal maps. You have the disk, C, or the sphere. And here you recognize exactly the three geometries: hyperbolic geometry, Euclidean geometry, and of course spherical geometry. So that's something which extends to something much, much, say, deeper. Okay, so that was for brief discussion. So now I want to try a little bit to find conformal maps between domains. So the first thing I propose to do is to look at this domain and to try to map it to the upper half plane. So basically, the different examples are just here. The first are easy, and the second one will be useful in the remaining of the course. So does somebody has an idea about what is a conformal map between these two domains? Please help me on this one, because otherwise we are not going to achieve it. Sorry? Log. I go that direction. Okay, but it's not the log. Sorry? It's even simpler than the log. I mean, yeah, that's more exponentially. So that was the easiest one. Now somebody for the disk. So let's just write, perhaps I can do a nice picture. I will not do many of them, but let's try on this one. Just to look at what does it mean that it's conformal in this case. It means that if you take, let's say, these curves here, they intersect with orthogonal angle, an angle of pi over 2. And so here, when I send them here, I will find something like, so I will not find this, sorry. No, I will find this, sorry. I will find this kind of picture where here I still have an orthogonal angle. It's really what it means to be conformal conformal in this case. So for the second case, does somebody has an idea? Yesterday you were great, so carry on. How do you send this one to this one? Sorry? Yeah. So you want to put fraction. So I like, in order to try to find the conformal map, what I like to do is to try to send points on the boundary already to what I want. So what I'm going to do here, I'm going to send 1 to 0, say, and try to send the most natural one would be -1 to infinity. So natural things is to look at this kind of thing. This will send the right thing to the right thing. And you can check that if you are on the circle, it sends the circle on R. So I'm in good shape to have the right conformal map, except that I need an I here. And when you look, same thing as before, at maps like this, what can somebody guess what I will see here? The blue things, the blue circles, on which thing are they sent? So we are going to do a bet. So people say lines there. I will not, okay. Others say that. So what is that? An ellipse or more? I'm not saying it's wrong. I'm just saying I don't know what it is. Okay? Okay, so, sorry? So 0 is sent to I, yes. So I'm looking at the blue ones. They don't pass through, through 0. What is the shape of the blue one? Sorry? Something like this? More circle, more circle. OK, I knew that you had it, but OK. And, this is called a homography, and it sends circles to circles. So it's very easy to draw what is happening here. It's really nice circles. And because I know I'm orthogonal, these are of this kind. So this is the shape you get. OK? So that was for the kid examples. Now, one which will be very useful is this one. How do you map this domain, this slit domain, to this one? We will need that. Yes? OK, so first I square. Good idea. So when I square, I find, so this is a function, this square, I send to this map, yes. Yes. You add a plus r squared, so you move it to the right. And then square root. So you have to be careful when you take square roots for people that are not used to what it means, because here we are not in R. So what do you mean by square root? But the thing is that when you are on simply connected domains, it does not matter. You have what we call a determination of the square root. So for people who don't understand these statements, they come at the end and they ask me. I will explain. So finally, the map here is the square root of this square plus r squared. And that would be important. OK. Harder and harder when you want to start from the disk and you want to send it to the slit like this. 0 and -1/4. What can you do? I will accept two different answers. The one for people who don't know and the one for people who know. OK. So if you don't know what is the answer, I mean the right answer, you try to find a wrong answer, which is also right. But anyway, so you move it on the right. You take the square root. You are back in the upper half plane. And after, you map by the inverse of this to the disk. So you can give me, obviously, a function. But there is one which is much more natural, and what is called the Cobra function. And you will see that it's an important one, which is z over 1 minus z squared. So this function, as an exercise, you can try to check that it sends the disk to this slit domain. And what is the development in power series for this function at 0? If you want to write it as sum of an zn, what is an in this case? Sorry? N, yes. NZN. And you will see that this function is central in the theory. Sorry? Here, it's everything except this slit. Yes. Really is this. Yeah. Okay. So you can check that this function works. Okay. So I gave another example, but we will forget about it and directly go to the real man example. So I'm waiting for you. From the half plane to a polygon, but let's say to an equilateral triangle. And I like this example because it shows that this theorem is really non-trivial. Because if you want to find explicitly the functions, you are in pretty bad shape. That's very hard to find an explicit conformal map between two domains. And finally, the one here is the most general case you know. I mean, when you extend the idea we will use here. So it's really a pity somehow. So once again, if you really want to find this function, and that's a hard question, what you do is you start by looking at the boundary. You have R, and you want to send it to a polygon. And one way to send to a polygon is to do the following, to look at the derivative, and to look at the derivative that has constant argument. If I find a derivative which has piecewise constant argument, then it means that it goes straight on different intervals. So let's say that I put 2 points, one here and one here, minus 1 and 1. So I would like to have something constant here, which make a step here, constant here, step here, constant here. The argument, I mean, for the derivative. So what kind of function is holomorphic inside the domain, and when you look at what is happening on the boundary, it makes a step. The argument. So the answer is hard. So I'm sorry, today I cannot really, I can ask questions, but the theory itself is a little bit hard, so it would be more a course than a real TA. I'm sorry. I apologize for that. But so here, a good choice is to look at this kind of function, where alpha is something between 0 and 1. So what do I mean by that? Typically, here, think about perhaps the easiest one would be this. OK? So what do I mean by that? So let's take 0, perhaps. So this function, if I want to define it on the upper half plane, because I'm not positive number, I need to do something here non-trivial to define this. And when I'm in this upper half plane, it's actually easy. The square root is a reciprocal of the square. So if I have something which is called, if I have z which is equal to r e to the I theta, what I want to define for my square root is just square root of r e to the I theta over 2. OK? And actually, you can check that this function, defined like this, it's holomorphic, and I will call this the square root. OK? So I extend the square root to something which is not real by this definition. So now, what does it do when we are here? The square root here is just square root of r. But when I'm here, imagine that you are going to this boundary. You are closer and closer here. I will get square root of r, so square root of, let's call it x on this side, square root of x, times e to the I theta over 2. but theta in this case is pi. So I don't get square root of the modulus, but I get I times square root of the modulus in this case. Okay? So I guess most of you are familiar with this kind of thing. So perhaps I'm saying that for nobody. But anyway, the argument here it's 0, and here it's I. And I make a step exactly at this point. Okay? And the step is exactly of angle pi over 2. So if I want an angle of, say, pi alpha, I will need to put here alpha. So now here, what I want to do in this case, and I want to do an angle which is 2 pi over 3. So what I want to take as an alpha is 2/3. So the derivative of my function should be something like 1 over z. So I want to do something here. I want to make a jump at this point, so z to the 2/3. And I want to make another jump here at 1, 0 minus 1 to the 2/3. If I look at this derivative, it's exactly constant here. The argument is constant here. It changed here, but it's constant here, and constant here. And it made steps. This is what I want for f prime. So if I take the integral of that, I will get something which maps the upper half plane to the triangular, the equilateral triangle. So if I take the primitive of this ugly thing, this thing, now you can just trust me if you don't get the motivation why it was natural to introduce this. If I take this form, this is a conformal map from this to this. So of course, I didn't prove it. So this function is holomorphic. Do you agree with that? I mean, that's the integral of a holomorphic function. It maps the boundary on the boundary, which is already something. And the thing is that when I look at that on R, what I see is that the derivative is always going in one direction, so that this function on the boundary, it's 1-to-1. So here we start to need the heavy machinery, which is in this theory of holomorphic functions. Because there is something that tells you, and that's not very hard, but I don't have time, I guess, to explain, that when you are 1-to-1 on the boundary, then automatically you are 1-to-1 inside. That's one of these magic properties, these rigid properties of conformal map. So this map is holomorphic. It's 1-to-1 on the boundary. And this implies that that's conformal between the two domains. And the imply here, it's not hard if you know enough of theory, but if you don't, that's impossible to do. OK, so just usually we don't take 0, but -1 here. And so we will get something like this. So this is a map that will be very important in the Cardis formula. OK? There are more general cases than this one. If you take whatever polygon, you can choose the alpha here in such a way that your map will be of this form. Where alpha and so on will be chosen exactly to be the angle of your polygon. And it works in this case. So that's called a Schwarz-Christoffel map. Just for the culture, it appears in many things, actually. OK, so now we need to look at two very important things. So if you didn't get this, it's OK. It will not be that useful. But now there is two important properties. So the first one is y not equal to c. So can somebody tell me why, say, the disk cannot be mapped to C by a conformal map? Yes? Yes, if you look at the inverse of this function, the inverse here will be a map defined on C, which is bounded. And such a map, by UV theorem, is necessarily constant, so far from being conformal. OK? So another example where you really need a non-trivial theorem. So you need to be different of C. And for the sphere, you have the same thing because the sphere is compact. And here you are open. So you cannot be isomorphic to the sphere if you want to look at the generalization. So other question, why, if I take D, which is simply connected, f of D will be simply connected? Yes, again. Sorry, I cannot hear you. Yeah. Yeah, that's a property which is shared by all the homomorphism. If you take you take the image of D, so you have two domains. D is simply connected, and you take f of D, where f is an homomorphism. So you want to prove that f of D is simply connected. What you do is you take a path, a closed path in your new domain. You map it back to D. That's a path in D. This one can be retracted to one point. But the way you retract this path to one point, when you map this way to the new domain, it exactly gives you a way to retract the former path to a point. So I don't want to spend too many time on that. But that's not specific to conformal maps. OK. So it shows that somehow that's exactly the perfect conditions. And now there is an important thing, which is the question of unicity of your function. Uniqueness, sorry. So is your function unique when you take two domains, D and D prime? How many functions do you have from D to D prime? And that will be very important in our theory. So if I want to count the number of functions from D to D prime, it's sufficient to look at functions from D to D, where D is a disk. Why? Because if you have the number of functions, since you know that there is at least one function from D to the disk and one function from D prime to the disk, you can map everything to the disk and only work in the disk. So do you know functions that are conformal and map the disk to the disk? Sorry? Rotations, yes. So that's an example. Can somebody give me another example? Yes, yes, yes. I'm just looking for a function from D to D. No, not again. Sorry? Yeah, all the Mobius transform. So the Mobius transform, they are of this form. That's the composition of a rotation with this map, where A is any point in the disk, inside the disk. And you can check that these functions, they send D to D. The fact that they are holomorphic is obvious, and actually, so perhaps I will call that phi of theta A. It's easy to check that phi of minus theta e to the I theta A is the inverse. There is a natural structure of group on these maps. OK. So there are more than one function, one conformal map from D to D prime. But the question now is that if you fix some conditions, you will have uniqueness. And what I want to discuss is what kind of conditions you can fix. So the first kind of condition, so here you see you have a certain degree of freedom, which is theta and A. So A is a complex number, so basically it's 2 degrees of freedom, real degrees of freedom. And theta is another degree of freedom, real degree of freedom. So you have 3 degrees of freedom. So you need to fix 3 things. So what you can fix, and I will not, that's a very simple computation. You can fix the image of 0 and the argument of the derivative at 0. And that's completely obvious. You just have to find the theta and the A in such a way that you will map, say, phi of 0 to A, and phi prime of 0, say, real positive. And you see, fixing the argument is 1 degree of freedom, and fixing phi of 0 is 2 degrees of freedom, because you need 2 coordinates. OK? So that's the first thing you can do. Very simple computation. Another thing you can do is you can fix phi of 0 and phi of E of I theta for some theta. So basically, you can fix 1 point inside your domain and 1 point on the boundary. You send 0 to whatever point inside, and this point to whatever point on the boundary. And same thing, just a computation to check that you can do it. And the third case is that you can fix 3 points on the boundary. So you take 3 points. You can send to whatever 3 points here. OK? So really, what you will need during the course is this thing, that either you fix 3 points on the boundary, or 1 point inside and the direction of the derivative, or 1 point inside and 1 point on the boundary. OK? OK. So for instance, if you want a theorem for the uniqueness, you can say there exists a unique phi between D and D prime such that, I don't know, phi of omega equals omega prime, and phi prime of omega is strictly positive, for instance, for omega in D and omega prime in D prime. Basically, this kind of result is true. You have this kind of uniqueness. But you need to add something. You have 3 degrees of freedom. So far, this theorem, I didn't prove it because I found some functions that are conformal from D to D. but I didn't prove that they are the only one. So if I can prove that this, the Mobius transform, if the Mobius transform, Mobius maps are the only one from D to D, then this theorem is easy because basically you have only one Mobius transform that maps 0, say, to 0, and phi prime of 0 strictly positive. That's easy to check. I mean, here, when I want to fix that, I really have only one choice. And that's exactly what will give you the uniqueness here. So same thing in the course. We will need at some point to say, OK, we have two functions. They are both conformal, and they satisfy both that, say, these 3 points are sent to this exactly 3 points on the boundary. Then I can deduce they are equal. For instance, in Smirnov theorem, for percolation, it's very important. So what I need to prove is that that's unique. And I will do that after the first question of the next exercise. OK, so that was for the Riemann mapping theorem. To remember is only, you only have to remember that the conditions are exactly the one we need. We cannot weaken or in any way the theorem. That you have 3 degrees of freedom in the choice of your map. And the last thing, I don't know. Perhaps that's hard to find explicitly a function, a conformal map between 2 domains. So now the second exercise. You change completely the philosophy. You want to estimate the derivative of your function just using informations on the domain and the range. And that's really where you see that this kind of theory is very rigid, since that you have a lot of information only looking at this. And the first question, so that will be useful because we will do exactly the opposite. We will compute the derivative, and we will deduce information on the domain. Because ultimately, this kind of conformal maps, they won't be useful for us. What we want to really to capture is the domain itself. And so by having information on the conformal map, we will get information on the domain. And really, the right thing to look at is the derivative. So the first question is called Schwarz Lemma. And it says the following. So you take a function from the closed disk to the closed disk, which is continuous. And you further assume that f of 0 equals 0, and f is holomorphic in D. So you really imagine you have your function from D to D. It's holomorphic, and you can prolong it to the boundary. OK? What this Schwarz lemma says is that f of z, f prime of 0 in modulus is less or equal to 1. That's another formulation. It's better than what I put in the notes. So you can estimate the derivative at 0 just by looking at the domains inside which you are defined. OK? And it says even more than that. And if f prime of 0 is exactly of modulus 1, then f is a rotation. And this statement, it implies easily that the only a Mobius transform, the Mobius transforms are the only conformal map from D to D. But anyway, I'm really interested in this thing. Okay, so can somebody say how you do that? Somebody has an idea. Yes. Yes. Yes, exactly. So f of z, if you look at it like this, you know that that's an analytic function. We say that holomorphic functions are the same as analytic function. So you can write it as an infinite sum like this. And the fact that f of 0 equals 0, it exactly implies that it's of this form. A0 is equal to 0. A0 is exactly f of 0. So if I divide by z, I find a very nice function which is also holomorphic. So you should be just careful, prolong it at 0, but that's also an analytic function. Okay? But because it's an analytic function, it satisfies the maximum principle, which says that the maximum of an analytic function is necessarily on the boundary of your domain. And same thing, if you don't understand this statement, you come at the end. So it means that f of 0, so this function g of z, which is f of z of z, you have that the modulus of g of 0 is less or equal to the minimum, or the maximum in the case, of the g of z for z on the boundary of your disk. But g of z on the boundary of your disk, it's this. This I can forget about it, because on the boundary of my disk, the modulus is 1. And this is smaller or equal to 1 since I'm mapped to the disk. So this thing is smaller or equal to 1. And I did use g of 0 is exactly a1. So I did use that the modulus of a1 is less or equal to 1, and the modulus of a1 is exactly f prime of 0. Okay? So once again, yeah. Why f of z is? Because I assume that I'm mapped to D. So I have an information on my target space. And this information, I can translate it into an information for the derivative. So somehow, you cannot have as large a derivative as you want. So this thing was really, you have an information on your domain. You can deduce an information on your derivative. What I'm going to do now is a little bit the opposite. I mean, it will be useful in the opposite. Yes? Oh, thank you. If you have equality here, it means that the maximum is achieved inside the domain. And when the maximum is achieved inside the domain, it implies that the function, by the maximum principle, it implies that the function is constant. So once again, a big theorem which allows to derive this. OK, so now, Cobra 1/4 theorem. So this one is, it looks the same as the other one. You take a map from D to D prime. And what it says is that when I look at the derivative at some point omega, it's less or equal to 4 times the distance between f of omega and the boundary of D prime over the distance between omega and D. And here I have the same thing with 1/4. So what it says is that really you have 2 domains, perhaps an ugly one here, I don't know. If I take a point omega here, and I have 2 information I'm at my disposal, this 2, 1, then I can estimate the derivative of f. And I can estimate it pretty well because I have the 2 bounds. Okay? So this one was saying if you translate it, it was saying something like the derivative is less or equal to the distance of the target point to the boundary. And here you have something a little bit finer somehow. Sorry? Yes, sorry. So perhaps that would be simpler if I do like this. And that's, yeah. And in this case, it's very bad what I did, sorry, and f is conformal. OK. So that will be really the main tool in the study of SLE. And so probably what I did so far was too fast for people who never saw it, and it was too slow for people who already saw it. So I was thinking first that the first part would be for people who never saw complex analysis, and this part for people who already saw, but I guess. So this one is going to be a little bit more tricky, but the road we are going to take, you will see, we use theorems that are really related to Loeffner evolution somehow. So as a historical, it has an historical interest. So the first step is to look, to try to bound. So we want to bound the derivative. Say we want to do the left side. The right side is exactly the same. We want to do the right side, sorry. The left side is exactly the same because you take the inverse function, and it will give you exactly this bound. So really, morally, you just need to prove one bound, this one. So you want to bound f prime of omega. So let's say omega is equal to 0. You want to bound f prime of 0. You want to bound the first coefficient. So you want to bound the coefficient. So how to bound the coefficient? That's a tricky question. One thing is to try to use what we call the area theorem. So first, what I'm going to do is I'm going to normalize everything here. Because you see there are too many things which depend on each other. So what I will do is that I will look at function f, which are from D to f of D. So they start from the whole disk. It's equivalent to say that. And I will fix f prime of 0. I will say f prime of 0 equals 1. So that the only thing I need to do now is to look at a bound for this. And namely, what I want to prove, so I will have failed aggregation doing like this, but so we want to prove the exact equivalent will be that the distance from 0 to the boundary of f of d is greater or equal to 1/4. If you do just the renormalization, you arrive to this thing. Trust me, that's completely elementary. So in other words, I want to prove that the ball of radius 1/4 is necessarily included in f of d. OK, so I look at this kind of function. By the way, they are called Schlicht functions. And if there is a German in the room, he will say that that's not like this that we write it, or I don't know. No, that's OK? OK. Yes? Yes, sorry. You really normalize everything you can, which doesn't cost anything. So this is the maximum renormalization you can do. And now you need to prove that the distance between 0 and the boundary is greater or equal to 1/4. Thank you. OK, and so what I was going to say is that you use what we call the area theorem. So let's say first that you have a function f defined on the disk, which sends the disk to some domain. Can you express the area of this domain? It's a conformal map. Can you express the area of this domain in terms of coefficients of f? See, I have something here. I want to compute this area. Can I do it just in terms of the coefficient of z, of f? This is yes, and it has a very nice form, which is the following. This is equal to that. So I assume that the image is bounded. And how you prove this? You just look at the integral along this path gamma, the boundary of z bar dz. This one form here, it's related by Stokes' theorem or Green theorem to the integral of the interior. So the interior will be called E of dx vectorial dy, so of the area. So that's like classic, I guess. When you look at this now, because gamma is the image of this circle, it's exactly the integral on the circle of f of e puissance e to the it bar, f prime of e to the it, I e to the it, it's too much I and e, dt. That's exactly what it means. I have a natural parameterization for gamma, which is given by f. And when you compute this, you develop in series, and you compute this thing, you exactly arrive with that. That's easy to do. It appears that you can do exactly the same thing, but with another function. So now I take f, a Schlicht function, and I look at f of 1 over z. So f sends the disk to something, perhaps non-bounded. F of 1 over z, it sends the complementary of the disk to the same thing. 1 over f of 1 over z. It sends the complementary of the disk to something. When you look at this function, and you apply exactly the same idea as here, you can compute the area of this thing. And what you will get, and what is a little bit what is magic, is that you get that the area of this it will be 1 minus sum of n. So it will be 1 minus sum of n bn. Where the bn are the power series development of this. So that's kind of a trick, which is just saying I start from a Schlicht function, I play with it, and at the end, I can compute an area. It's 1 minus this, where these are the coefficients. But the thing that this area, it's positive. I don't say anything new here. So it implies here that, say, B1 is smaller or equal to 1. So I have bound one coefficient. It's not the one I want, but I managed from F to be able to bound a coefficient which is obviously in some hidden way related to F. So that's really the tricky part of the proof. Yes? Yeah, you are mapping to the complement, sorry. So you are just, but when you do this thing, so you map to the complement, but you can forget about that. When you do the thing here, the same reasoning, what you are going to compute is what is inside, which is the complement, but it's positive. Yes, that's true that you map to the complement. And it's not the same shape here and here. OK? But OK, let's forget about the proof itself. Let's say that the philosophy is already here, in the sense that you have a domain, and you have used it in some hidden way to get something which is positive, and it gives you a bound for B1. So now what is the hint? What do we want to do? We want to construct a function, starting from this, to construct a function such that B1 will be equal to A2 over 2. If I can construct a function like this, then I won, because I proved that. So sorry, I did not win, but I will be able to bound a coefficient for F this time. So I guess looking at your face, yes?
It's a bound of B1, but also on the other B. Right?
Yes, on a lot of B's. Yeah, all the B's, you have a bound for them, if you want. Yeah. It won't be useful for us, but it's true. And I will come back to this later. So you want to construct something, a function, such that the B1 will be A2 over 2. And yes? This one or this one? This one. It's exactly the same reasoning. So I mean, here I cheated more than once in this proof, because I don't know if the function is holomorphic on the boundary. I just assumed that it was holomorphic inside. So first, you have to be careful about that. But you can rule out this thing. But and here, I didn't do the computation. But exactly the same reasoning applied to this weird function works. So you just have to think you can do it by yourself. Yes? This function is homotectic. This, what is that? I'm sorry, I didn't. Yes? Yes. But I mean, you didn't use, when you look at this line, green theorem or Stokes' formula, you don't use the fact that the interior is the interior of your domain. Not at all. So here you will do the same thing on the boundary, but it won't compute what is outside. It will compute what is inside. OK? So it's not related to the interior or the exterior. We don't care. It's what is inside. But what you use is that it's one-to-one, because you don't want to compute. You are computing a algebraic area. So you need to be able to relate it to the real area. So this construction, it's a little bit tricky, but it's completely elementary. And I gave a hint in the TA, in the exercises. It's easy to do, really. You construct it. It works. So somehow, from F in S, what you construct is a G in S, but which has this development. Plus something. That's not very hard to do. And this, when you take 1 over G of 1 over Z, you get exactly Z plus 0, actually, and minus A2 over 2 times 1 over Z plus so on. So the A1 is A2 over 2. OK? But this is not the hard part of the proof. So you can construct this G, which exactly gives you that A2 is less or equal to 2. And that's something very important. It's the first step of what is called the Bieber-Bach conjecture. So by the way, the proof of the Cobra theorem, it's not due to Cobra. That was a conjecture by Cobra, and it was proved by Bieber-Bach. So the Bieber-Bach conjecture it says a very nice thing, the very nice following thing. You take f a Schlicht function, then an is less or equal to n. So a Schlicht function, remember, it's just a function for the disk to something. So it's a one-to-one function. We don't specify where we are arriving, such that f of 0 equals 0 and f prime of 0 equals 1. Then, if you have this property, Bieber-Bach conjectures that an is smaller or equal to n. So what we did here is we proved the first step, step n equals 2. OK? Lovner proved the case n equals 3 using the Lovner evolution. So he introduced the Lovner evolution in order to prove the case n equals 3 of that. So Bieber-Bach proved A2 less or equal to 2, and I didn't, but almost. Lovner proved A3 less or equal to 3 using the Lovner evolution. So that's a historical introduction. Just for the story, Littlewood, so that was in 23. in 25, little rule proves the following thing. an is less or equal to e times n. So up to constant, he had already the conjecture. So some people improved that, but finally it was De Branche in 85 who proved the complete conjecture. So now it's a theorem. And he also uses Loeffner evolution. So that was for the story. You see, the world is a little bit small in this domain. You see the same kind of people, same people everywhere. OK, so how do we conclude? Now that we have A2 smaller or equal to 2, that's the next question, I guess. Yes. So what we wanted to do, remember, is to prove that, and we say that it was sufficient to prove that. So we are not assuming anything on the target point, a target domain, but we want to prove that the ball of radius 1/4 is inside it. So the thing that we are going to do, we take Z0, which is not. So we have f in S. And we take Z0, which is not in f of d. And we want to prove that its radius is larger than its modulus is larger than 1/4. So that's a little bit always the same trick. When you have something which is not in your domain, you like to divide by f minus this thing. So you divide by this. And you want to construct a function in S from this. So you take f of z. So this function, it's a function defined on the disk. It is equal to 0 at 0. The only thing is that it's not necessarily of derivative 1. And so to get the derivative 1, it's z0 or minus z0. I don't know, plus or minus. Right. So this is a function which is also in S. But when you do the development of this function, you obtain that. Once again, it's simple computation. So this thing is smaller or equal to 2, which exactly implies that 1 over z0 is less or equal to 4. Modulo of z0 is larger or equal to 1 over 4. If you think this is a weird technique to do that, it's exactly the techniques that are used in Riemann mapping theorem to prove the Riemann mapping theorem. And that's things that are very classical. So because you have this, and that will be very useful for us because looking at the derivative is basically looking at how far we are from the boundary. So that was all for today. This Riemann mapping theorem that will be useful will be, what we will do is we will take weird domains, and every time we would like to map them back to a very nice domain. So we will need always this Riemann mapping theorem. And the thing is that we will do it in a canonical way, and this canonical way will be to fix the boundary condition, to fix these three parameters. So it was very important to get the fact that you have 3 parameters. If you must retain only one thing, it will be that. And for the second part, the important thing is that if you have estimates, if you know the shape of your domains, you can get an estimate for f prime and vice versa. And that will be the second thing that we will use a lot of time. Thank you. So for people who have questions about all this dark magic that I use, you come and you ask me.